All right, let's get right into it. If you've ever worked in robotics, you know this feeling all too well. You give a robot what seems like a simple, high-level command, and it just fumbles. That space between what a human means and what a robot actually does, well, that's one of the biggest hurdles in the entire field. Today, we're going to break down a really clever new approach that's finally starting to bridge that gap.
I mean, it's the kind of question that keeps engineers up at night, right? How can this incredibly sophisticated machine, packed with sensors and actuators, fail at a task a toddler could probably handle? The thing is, it's not really a problem of intelligence. It's a problem of context, a lack of being truly grounded in the physical world. This image here, this gets right to the heart of it. A command like, fetch coffee, seems so simple to us. But for a robot, it's this cascade of questions. Which cup? The one on the left? Grab it from the handle? How much force should I use? This disconnect between a big picture goal and the tiny, precise physical steps needed to get there, that's what we call the grounding gap. Okay, so let's formally define this thing. The grounding gap isn't just one single problem. It's actually a trio of related issues that can plague even the most advanced robotic systems we have today. So the grounding gap really boils down to three main culprits. First, there's the vision-action disconnect. A visual language model, a VLM, can look at a scene and create a to-do list, but it struggles to give the robot the exact coordinates for where to put its gripper. This leads to the second issue, action hallucination, and yes, that's the real term. The VLM literally just invents steps that are physically impossible. And finally, it all comes back to those ambiguous instructions, where a simple human phrase just doesn't have the hard data a robot needs to actually do something. But here's the good news. There's a really powerful new solution starting to emerge, and it doesn't try to solve this by creating one perfect, all-knowing model. Instead, it uses a clever hybrid system that plays to the unique strengths of different AI and planning techniques. And here's a look at the system's architecture. It all starts on the left with video demonstrations. These feed a massive library of over 40,000 spatial lessons. A VLM then uses all that knowledge to come up with a high-level plan. Then, and this is the key, that plan is translated into a language a classical planner can solve, which results in a precise, executable action for the robot. It's a really powerful combo of modern AI and good old-fashioned robotics. We can break that whole flow down into three simple steps: see, translate, and plan. First, the system sees. It learns from watching thousands of video examples. Second, it translates that visual info into a symbolic, big-picture plan using a VLM. And finally, it plans, using a deterministic, classical PDDL solver to turn that general idea into a rock-solid, step-by-step sequence of actions. Now, that C part of the system is called Video to Spatially Grounded Planning, or V2GP. The real genius here is its simplicity. By watching videos and just looking for when a hand opens or closes, it can figure out the intent to either grasp or release an object. From just that simple cue, it's built up a library of over 40,000 spatial lessons. It's how it grounds all its potential actions in actual physics. The other key piece of the puzzle is the hybrid planner itself. It lets the VLM do what it's amazing at: generalizing, understanding context, and creating a broad strategy. But then it hands off the final, nitty-gritty tactical plan to a classical solver. And that solver doesn't hallucinate. It's guaranteed to produce a plan that's actually logically possible. What you end up with is this perfect partnership. Think of the VLM as the creative strategist on the left. It figures out what needs to be done. The PDDL solver on the right is the meticulous engineer. It figures out exactly how to do it with a precise, reliable plan. You get the flexibility of modern AI with the dependability of classical robotics. So, the architecture is elegant, no doubt. But does it actually work? Let's take a look at the numbers, because the jump in performance here is, well, it's pretty staggering. This is really the ultimate question for any new system, isn't it? It's one thing for an idea to look good on a whiteboard, but how does it hold up when you throw complex, real-world tasks at it? Well, the results are like night and day. On a whole bunch of complex tasks, the baseline models, the ones that rely only on an end-to-end VLM, they topped out at a success rate of about 30%. This new hybrid system, it more than doubled that, hitting a 70% success rate. Let's just let that number sit for a second. 70%. In the world of robotics, an improvement of this size isn't just an improvement, it's a massive leap forward. It's a fundamental shift from a system that fails most of the time to one that succeeds most of the time. And for all the engineers watching, I know what you're thinking. No, this wasn't some tiny, cherry-picked test. This data comes from a really robust benchmark called Grounded Plan Bench. We're talking over 1,000 real-world tasks across more than 300 different scenarios, all specifically designed to challenge robots with vague instructions.
A 70% success rate is fantastic, but what does that actually mean when it comes to deploying hardware out in the field? This is where a theoretical breakthrough becomes real-world value.
When you start looking at the key metrics for automated systems, like the ones used in self-driving labs, the benefits become crystal clear. A higher degree of autonomy means less babysitting from human engineers. A longer operational lifetime means the robot can just keep working without getting stuck. And higher throughput and precision, that just means you get more done more reliably and for less money. This system improves performance across the entire board.
And the results from field testing really drive this home. The system is great at those long horizon tasks, things with 9 or more steps that have always been tough for AI. In some tests, models using V2GP hit an incredible 93.3% action recall rate. And, maybe most importantly, it's starting to master implicit instruction. It can hear a command like clean up and actually infer all the little steps required to do it. So this hybrid approach really seems to be closing that grounding gap, turning our ambiguous intentions into precise, successful actions. It is a huge step forward, and it leaves us with a really fascinating question. As robots get better and better at understanding and doing what we want in the real world, what tasks that were once only for humans will they be able to take on next?